The idea that the Earth rotates around its axis was born in ancient Greece, and it suffered a great deal of criticism for many centuries, until it was finally proven in 1851 by Léon Foucault. However, there are still people who doubt it.
But one thing we all agree on is that we don't live on a spinning ball flying through infinite space.
Do you feel yourself spinning, wobbling, gyrating? No, I'm pretty rock solid.
We always say, don't believe us, do your own research.
Okay, that's exactly what I'm going to do. So let's have a closer look at how we can describe circular motion. If we have an object spinning in a circle of radius r, we have the tangential velocity and the centripetal force pulling on it towards the center of the motion. If we add a mass m, then the centripetal force will be m times v squared divided by r, if we observe from a stationary frame. If we now observe from the center of the motion, i.e. a rotating frame of reference, such as on a merry-go-round, we notice the object being pulled away by the centrifugal force, which is equal in value to the aforementioned centripetal force. Now this is the case which applies to us on the spinning globe, since we rotate with it. To calculate the magnitude of this force, let's firstly see about this tangential velocity. Considering the circumference of the Earth of 40,000 kilometers, and knowing it performs a complete rotation in one day, we find the tangential velocity is 1,667 kilometers an hour at the equator. So we take the value of the tangential velocity, and considering an average person weighing 70 kilograms, we find the centrifugal force is 2.35 newtons at the equator, which is equivalent to the weight of roughly 240 grams. But for the same person, the gravity pulling towards the center of the Earth, or opposite to the centrifugal force, is 686 newtons, which is about 300 times larger than the centrifugal force, once again at the equator. The reason I keep mentioning this is that both the tangential velocity and the radius vary with the position on the globe. One thing that's constant wherever you are, however, is the 24-hour day. Now, if the Earth rotates 360 degrees in one day, it means its angular velocity is 15 degrees an hour, and this is constant. The angular velocity is defined as the tangential velocity over the radius, so we can rewrite the centrifugal force as a function of angular velocity. The force, as we can see, varies linearly with the radius, being largest at the equator and decreasing to zero at the North Pole. This is the reason why the Earth is an oblate spheroid and not a perfect sphere. But we're getting off topic. So we see that the centrifugal force is not nearly large enough to pull anything from the surface of the Earth. However, I came upon this incredible comparison.
So imagine spinning at 1,000 mile/hour at the edge of a roundabout, how tight you'd have to hold on.
I feel like I'm holding on pretty tight now.
Before we jump to any conclusions, let's just describe what happens when you drive in a roundabout. So we have the car with the centrifugal force always pulling outwards. If we again consider a 70 kilogram person driving at 20 kilometers an hour, the centrifugal force turns out to be 100 times larger than the one felt at the equator. To feel the same force, you'd have to drive at 2 kilometers an hour and not 1,000 miles an hour as he said, which means it would take you almost 2 minutes to do the whole roundabout. The only thing you'd feel in this case is the annoyed driver's horns. But let's return to our planet. In this animation, the Earth spins much faster than it actually does. In reality, the motion looks like this. Believe it or not, it's still rotating, but very, very slowly, as a complete rotation takes 24 hours. But let's try to find how much faster it should rotate for people to start falling off at the equator. For that to happen, the centrifugal force needs to overcome gravity, so the tangential velocity would be 23 times the speed of sound in air. This means that a day would only last for roughly 1.5 hours. Now the motion looks like this, noticeable but barely, because of the planet's massive size. Since we all agree that a day is 24 hours long, let's see how much bigger our planet needs to be to fall off at the equator. The new radius turns out to be almost 2 million kilometers, which would mean that the distance from Thailand to Peru becomes roughly 6 million kilometers. To understand how large that is, if you made a phone call between those countries, you'd have a 20-second time delay, because that's how much it takes light to travel that great a distance.
But one thing we all agree on is that we don't live on a spinning ball flying through infinite space. We always say, don't believe us, do your own research.
Well, you were right recommending not to believe you. As it turns out, we cannot fall off because of the Earth's rotation.